We are working within microfluidics. So our setups have sizes of the order of 10 to about 400 microns. So applications, there are many. Well, inkjet printing is one of them, sequencing and separation of macromolecules. But our main interest is, in fact, microrheology, the measurement of extensional viscosity for fairly dilute solutions is quite difficult using classical methods. And we want to develop microrheometers for measuring this extensional viscosity, which I will introduce to you in a moment. Because of our scales, as I said, geometries from about 10 to 400 microns, we are clearly in a domain where the classical equations are valid. So no need to account for slip and other effects that you sometimes need to account for observed phenomena. If you try to make a list of fluids that you know on a piece of paper, so you split it in two, on one side you write names of Newtonian fluids and on the other of non-Newtonian fluids, it's interesting that very quickly you run out of examples of Newtonian fluids, and yet the list of non-Newtonian fluids is quite vast. Of course, in the biosphere, water and air are largely found in overwhelming quantities. But in fact, the number of fluids that are Newtonian are not so much as you may think initially. Anything dealing with multiphase, macromolecules, particles, so becomes quickly nonlinear in behavior. And of course, this keeps increasing every time because engineers have this habit of developing fluids for particular applications. And so these are usually non-Newtonian. Talking about properties, of course, viscosity is a very important one, and shear thinning is very typical of polymer solutions, so the viscosity goes down as the shear rate increases. In this film, initially you have a Newtonian and a shear thinning fluid with the same apparent viscosity. You can see that they flow at the same time. Then you increase the pressure, and this results in an increase in the overall flow rate, so the shear rate will increase, the viscosity decreases, and now the shear thinning fluid flows faster, okay? So many polymer solutions tend to be shear thinning, although sometimes you can manufacture elastic fluids which have a constant viscosity, the so-called Boga fluids. Of more interest to this talk are elastic effects, and we have here on the left the so-called Weissenberg effect. Initially you have a Newtonian fluid, with this concavity. There is a rod rotating inside the beaker. Of course, there is this depression because of centrifugal effects. Polymer was added. Now it's going to dissolve, hydrate, and the fluid becomes viscoelastic. And because it's viscoelastic, there will be shear-induced normal stresses, which will try to strangle the rod, and as a consequence, the fluid will rise along the rod. This is a nonlinear elastic effect caused by normal stresses. You have here the property which is called the first normal stress coefficient, which is the difference between the two first normal stresses divided by the square of the shear rate. I think more spectacular is a demonstration of the extensional viscosity or the strain hardening of the extensional viscosity, which allows you to make an open siphon. So no tube, and you can have a siphon. The fluid, a Newtonian fluid has an extensional viscosity which is 3 times the shear viscosity, but a polymer solution, because of the presence of macromolecules which are being extended, can have extensional viscosities which are very, very large, of the order of 100 and even more than that. And because of that, the filament over a short period of time does not break, and you can make this open siphon or tubeless siphon. It's exactly for the purpose of measuring this extensional viscosity that we are interested in microfluidics, in developing the microrheometers. Governing equations, of course, the continuity equation is the same. We are assuming fluids are incompressible. And then the Cauchy equation, momentum equation in the Cauchy form is, of course, the same. And then the stress, the extra stress tensor, has to be given by an appropriate rheological constitutive equation. For instance, total stress, which is the sum of a solvent contribution plus an additive contribution coming from the polymer. Sometimes, if you are working with a polymer melt, you can eliminate the contribution from the solvent. You just have the polymer stress. This is a general equation. It's a very long differential equation on the stress. Includes several models. So let's simplify. Let's eliminate this term there. Let's make also this parameter xi equal to 0 and this function equal to 1. So you just have the stress, the relaxation time multiplying a convective derivative of the stress. What is important here is that you have three nonlinear terms, the classical advective term, but two new terms associated with the convective derivative, which are called the distortion terms. And if you think about a flow in the limit of low Reynolds number, so the inertial nonlinear term in the momentum equation goes to 0, disappears, and what remains are these two terms, the distortion terms, and these are going to be the sources of instabilities in viscoelastic fluids. Okay, so you can have unstable flows, or even some people are looking for elastic turbulence, meaning turbulence at 0 Reynolds number. That comes from these terms, or even if psi is non-zero, also from these other terms, which couple stress and velocity within the constant equation. Relevant dimensionless numbers, of course, you have the Reynolds number, and then you have two numbers involving the relaxation time, lambda. One is the Deborah number, which is the ratio between a relaxation time and of the fluid and the characteristic time of the flow. The Deborah number is used for to express, let us say, transient phenomena, variations with time. The Weissenberg number is more commonly used to express phenomena which involve elasticity, but in steady flow, like shear-induced normal stresses, for instance. So you have the relaxation time. Relaxation time multiplied by the strain rate, and which gives essentially a ratio of normal to shear stresses. As you can see at the end, the Deborah and Weissenberg numbers look the same. That gives rise to some confusion, but of course, Weissenberg number is one thing, Deborah number is another thing. Sometimes it's important, the Deborah number, other times the Weissenberg number. And in occasions, both numbers are important. In that case, they are related by a geometric factor. In microfluidics, you often have to mix reagents, so mix tends to be difficult because you don't have turbulence, you don't have also chaotic advection if the Reynolds number is very small, unless, of course, you force it. So mixing becomes difficult, but if you add macromolecules and you give to the fluid viscoelasticity, you create sources of instabilities. So viscoelastic fluid instabilities will be important for enhanced mixing, and also important for people like us that want to develop microrheometers where the flow has to be controllable. In that case, the instabilities define the end of the operational conditions for the microrheometers. Okay. Another important thing, I will come back to that in a moment, is of course that the Reynolds varies in direct proportion with L, and Deborah and Weissenberg number in inverse proportion. I will come soon to that. Past work on elastic instabilities, well, there's been a lot of work in the past, but let's say that the modern view of viscoelastic instability started with the paper by Larsen, Schakfe, and Susan Müller in 1990. They investigated telequet flow. They concluded that the viscoelastic instabilities in telequet flow was a linear instability, and they showed it both experimentally and theoretically. Then there was other works by that group, and also then by the MIT group. Well, I think at that time McKinley was in Harvard, but McKinley's work on cone plate and lead-driven cavity flow, so progressively more complex flows. And all these flows were shown to be linearly unstable. Then in 1996, McKinley and Pactel, they wrapped up the various criteria into a simple relation of quantities, which is this one. I will come to you in a moment. But essentially, they say that whenever you have a curved streamline and normal stresses along these curved streamlines, you are bound to have an instability. Subsequently, more work I'm not going to talk further on this, but people started to look into elastic turbulence. So you have the contributions of Groisman and Steinberg, and there's a nice review in 2005 by Squires and Quake on microfluidics and viscoelasticity. So the criterion of Pactel and McKinley, which is this expression here, basically this applies to, so far, to a wide range of flows, constitutive equations, and of course the value of this M critical is flow dependent. Initially, the works were done with essentially 1D flows, like the Taylor wet flow, and progressively, as I said, more complex flows. This has also been tried in with various constitutive models. Basically, what it says is that the length scale for decay of perturbations divided by the streamline rays of curvature and multiplied by the stress ratio has to be higher than a critical value. You can understand that if you take, for instance, this picture. You can see this picture. So you have a flow, a rotating flow. Then if there is a perturbation and the streamline assumes this form, then the normal stresses are stronger the closer you are to the rotating cylinder. So in the end, this mechanism, the Northern stress mechanism, actually tends to enhance the instability, and the streamline will not go back to the circular shape initially, and the flow becomes, of course, unstable. Going back to the dimensionless numbers, the Reynolds number, Weissenberg number, or Deborah number, you can actually combine them into a single number where the velocity disappears. It's called the elasticity number. Now, this phase diagram belongs to the flow in a southern contraction, and you can see why, if you do experiments at large scale, so let us say macro fluid mechanics, you are bound to have large Reynolds numbers and small Weissenberg numbers. And so you end up here where the flow is stable. Of course, then it may become turbulent, but at high Reynolds numbers. I call that, when you are looking at laminar flows, boring fluid mechanics. But if instead you go to microfluidics, what happens is that this goes down and Weissenberg number goes up, and of course the Reynolds goes down, and then you work in here, and so you can have very low Reynolds numbers and very large Weissenberg numbers, and you go through a series of transitions, which I will show you later. So I call this the exciting fluid mechanics. Okay. As I said, we do experiments. We don't have, I mean, our microfabrication facilities are very simple. Most of the things have to be manufactured outside the university, even outside Portugal. But anyway, we manufacture using soft lithography. So you essentially have a silicon wafer, you spin coat photoresist, and you shine ultraviolet light to cross-link molecules, and you bake, wash out. And in this way, you produce a mold of the geometries that you want to make. And now you pour PDMS, cure it, and then put a cover slip, and you got the channels that you want to investigate. Okay. Then, of course, this is a mask compared with the still existing euro coin. A mask, you can put in a small mask a lot of geometries. This one is 20 geometries, so it gives you enough geometries for maybe 1 or 2 years of work. And then these are pictures taken on a scanning electron microscope of various geometries. As you can see, the quality is quite good, and you need actually a good quality, otherwise you'll have perturbations introduced by the geometry rather than by the flow. Depending on the additives you put, you can have walls which are nearly perpendicular. So these are the hyperbolic contractions. More pictures, in this case of a microfluidic diode, which is a series of hyperbolic contractions, and that is another microfluidic diode developed by Grossman Quake based on triangular setups. Okay, then we do essentially strict line imaging, micro PIV, pressure measurements, that's it.